Now we discuss the topic today, number systems in computer. See, students, you are already familiar with decimal number system. What is decimal number system? It is a base 10 system, which means that it considers the decimal digits from 0, 1 to 9. So these are the 10 decimal digits, and we form other numbers in the decimal number system using one or more combination of these digits. So that is decimal number system that you know. But in computers, we use other type of systems like binary number systems, okay, and octal number system and hexadecimal number system. These are the number systems that are most popularly used in computer. What is this binary number system? Binary number system is a base 2 system. Base 2 system means it contains two binary digits only, 0 and 1. Similarly, octal is a base 8 system which consists of 8 digits from 0, 1 to up to 7. And hexadecimal system, it is a base 16 system which contains digits from 0 to 9 and then symbols from A to F. A to F. Okay, A representing 10, B representing 11, and C representing 12, D representing 13, E representing 14, and F representing 15. So this is a base 16 system from 0 to 9 and then A to F. So these are the number systems that are used in computers. Stop. Now let us understand the conversion from binary to decimal, okay, and then from decimal to binary. First understand the conversion from binary to decimal. Suppose we have a number in binary digits like 10 and 11 in binary. See, the subscript in the 2 tells that it is a number in binary system. Now let us see how it converts to decimal. So it is very easy conversion. We take the digits from least significant bit. This is the least significant bit of the integer part, and this is the most significant bit of the integer part. Most significant bit. Okay. Similarly, for the fractional part, this is most significant bit, and this is least significant bit. Okay. So let us do binary number to the decimal number in parts. First integer part and then fractional part. Now the integer part is 1101. So we start from the least significant bit, multiply it with 2 to the powers, with powers of 2, starting from 2 to the power 0, then 0 into 2 to the power 1, plus 1 into 2 to the power 2, plus 1 into 2 to the power 2. And we accumulate the sum. What is the sum? 1 plus 0 plus 4. Okay, so 1 2 to the power 3, 4 plus 8. So the sum is 8 4 12, 12 plus 1. 13. So this is the 13 in decimal. Now for the fractional part 0.11, we do this way. We multiply starting from the most significant bit in negative powers of 2. For example, 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2. This is most significant bit. Okay, it is multiplied with 2 to the power minus 1. Then the least significant bit, this is multiplied with negative power of 2, that is 2 to the power minus 2. And we get the sum as 0.5 plus 0.25, that means 0.75. So the number is 13.75 in decimal. So understood the conversion? Okay? Okay students, understood the conversion? Now understand the conversion from decimal to binary. Okay, so if you have a number in decimal, I have just switched from the whiteboard to the blackboard because of some problems. So let us understand the topic that we were discussing, decimal to binary conversion. Okay, decimal to binary. Now let us take one example. 27.16 is the number in decimal which you want to convert to the binary. Now let us consider integer and fraction part separately. Now for the integer part conversion to the binary number, we divide with 2. Now let us divide it first. 2 13 26, the remainder is 1. 2 6 12, remainder is 1. 2 3 6 divided by 3, remainder is 0. Then 2 3 is divided by 2 one time and the remainder is 1. So we stop when we get 1 at the last, or we get 0 at the last. We stop here. This is the last step. So this 1 is the last step, which is actually the quotient. This is the most significant bit of our result, and this is least significant. The one generated at the first step is the least significant bit of our result. So we write from the least significant bit to most significant bit, that is from left to right, 1 1 0 1 1. So this is our number in binary. So this is the conversion of the number in binary. This is the integer part. Let us do for fractional part also. Now for fractional parts, what we do, let us understand for fractional part. Now 0.16, now multiply with 2, we get 0.32. We take the integer part 0 at outside, then again we multiply 0.32 with 2, we get 0.64. We take the integer part, that is 0, outside, then we take 0.64 into 2, this gives me 248, 2612, 1.28. Now the integer part is 1, so we take integer part out. Okay, so in this way, suppose we want up to this precision only, 3-digit precision is sufficient. Now this 0 at the first step is the most significant bit, and this 1 at the last step is the least significant. Compare it to the conversion of decimal to binary of the integer part. In integer part we were getting least significant bit first, and then going towards the left we were getting most significant bit, but here we are getting in reverse order. We get first the most significant bit, then towards the right we go on getting the next significant bits, and the last we get the least significant bit. So we get the number as 001. We write from most significant bit to least significant bit from left to right. So this is the equivalent result in binary of the fractional part. So this we get in the fractional part. Okay. Consider the conversion from octal to decimal. Now again octal to decimal. Let us take a octal number like 76 in base 8. Octal is a base 8 system. Now let us convert this number into decimal. Now let us say how do we convert from this octal number to decimal. Now the process is similar to the process where we converted from binary to decimal. How we converted from binary to decimal? See, we convert from binary to decimal by multiplying the individual bits of the binary number with powers of 2, and we do the same process here also. Suppose 76 is the number, and we go on taking the first digit 6, we multiply with 8 to the power 0. Okay, then next bit is, so let us do the process again. We take 6 multiply with 8 to the power 0. Next octal digit is 7, we multiply 8 to the power 1, and so on. If we get more digits, we go on multiplying with powers of 8 in increasing order. Okay, so we get the result as 6 plus 56, which is 62. So this is equivalent to 62 in decimal. Okay, now let us understand the conversion for the fractional part. Let us take one fractional part like 0.63 in octal. Let us convert it into decimal. So we now let us understand the conversion from octal to decimal. Now let us do the conversion from octal to decimal. So the process is similar to conversion of octal to binary. We take the number 0.63, which is the fractional part, we multiply it with 8. Now 0.63 multiplied 8 gives me 324 at 648 50. So this is 5.04. We take the integer part of this as 5, and we take the fractional part 0.04 and again multiply it with 8. So it gives me 30.32. So the integer part is 0. Again 0.32, take the fractional part, multiply it with 8, we get 8 to 16, 1, 8, 3, 24 is 25. So we get 2.56. So the integer part is 2. And the process is similar. Again, if you want a result of to more than 3-digit precision, we again take the fractional part, that is 0.56, and multiply with 8, accumulating the integer part at every step. Okay, so the result is now, so what is the result? The result, this is the most significant bit, okay, and this is the least significant bit. So we write result from most significant bit to the least significant bit, that is 0.50. This is equivalent to decimal value. Like 2, 5, okay, and we need to convert it to octal. See, the process is similar to conversion from decimal to binary. See, when we convert from decimal to binary, what is our process? When we convert from decimal to binary, we go on dividing the numbers by 2 and accumulate the remainders from right to left, means from the least significant to most significant bit, and this conversion from decimal to octal, it also takes the same process. For example, we go on dividing by it with the 8. So first we divide 8 3 24, so we get 1 as the remainder. Now see, we are getting 3 in the very first place, we are getting 3. So if we divide 3 by 8, it will give the remainder as 3 itself, because now 3 is less than 8, so we stop at the value which is less than 8. Okay, so this 3 becomes the most significant bit, and 1 is the least significant bit. So this conversion is 1 3. This is in octal system. Okay, so now you got the point how we convert from decimal to octal. Similarly for the fractional part, suppose we have a fractional part, like for example we have a fractional point 0.12 in decimal, and we need to convert it to the octal. So now we do the process that we did in case of binary system. For example, 0.12 is multiplied with 8, so we get it to 16. 0.96, we take the integer part of this, that is 0. Then we take 0.96 into 8, and we get 86, 48, 489, 72, 76, 7.68. So we get the integer part, which is 7. So we accumulate. Suppose we need up to 2 decimal points only, so we stop here. If we need more decimal points, we go on doing this multiplication like 0.68. We take in the next step 0.68 multiplied with 8 and get the value and take the integer part and so on. So the result will be equivalent to point. Now this 0 with the most significant bit, 7 with the next significant bit, that is 0.07, and you get in the 0.07 in octal. So this is how we convert the fractional part of the decimal number to the equivalent octal number system. Start. See, the way we are doing the conversion from decimal to octal. Similarly, we can achieve the conversion from decimal to hexadecimal. In the conversion from decimal to hexadecimal, the thing that will be changed will be instead of dividing it, we will divide by 16 for the integer part. For the fractional part, we will multiply with 16. The process will be same. We will accumulate the integer remainders, and we will accumulate the integer remainders at each step. Okay, now let us take one example of conversion from hexadecimal to binary and binary to hexadecimal. Now consider the conversion from hexadecimal to decimal. See, hexadecimal number, as I told you, it's a base 16 system. Now consider in hexadecimal number as 3b. Okay, now let us say how we convert it into the decimal part. See, the process is similar. We need to convert this number into the decimal system, which is like this. We go on multiplying this number with b, with the powers of 16. See, b represents what b represents. It is actually 11 in decimal. So 11 multiplied with 16 to the power 0, and 3 is multiplied with 16 to the power 1. And if we have more digits on the left hand side, we go on multiply them with the powers of 16. For example, suppose we have one more digit, then we multiply that digit with the 16 to the power 2 and so on. So the result we will get will 11 plus 48. 11 plus 48, that is 61. So this is equivalent to 61 in decimal. Okay. Now let us understand. Let us understand the conversion from. Let us first understand the conversion of fractional part also. Fractional part, suppose you have a fractional part dot a1 in hexadecimal, and you need to convert it to the decimal part. Again, the process is similar. We multiply a, the most significant bit, with 16 to the power minus 1, plus we multiply 1 and multiply 1 with the 16 to the power minus 2 with the negative powers of 16 and so on. And finally we do the sum of these values. A, in place of a we write 10 because a is equivalent to 10. So we multiply this 10 by 16 plus 1 by 16 square, which is 256. Then we take the sum of these values and we get the result. Okay, so this is the way why we do this. This is the process. Okay, you can do this calculation. This will be, you can easily calculate. This is not a big issue. Now understand the conversion from decimal to hexadecimal. See how we convert from hexadecimal to hexadecimal. Suppose the number we have 16. So in 10, and it's, or let's just say 76, and we want to convert it to the hexadecimal system. And let us understand this also, how we convert it to the hexadecimal system. So now conversion from hexadecimal system, again the process similar to the binary system. We divide it with the powers of we divide it with the with 16. 16, 6, 96, remainder is 10, and then again 6. Now 6 is a value which is less than 16, so we stop at this step only. See, we continue it to the step where we get a value which is less than the number which is less than the divisor. See, this 6, which is a quotient, is less than this divisor. We stop at this iteration or at this step. In the binary system also, if you remember, we stopped at the value where we get in the last 0 or 1 as the quotient. If we get the 1 as the quotient, we stop there because 1 is less than 16. Here we are getting a quotient which is less than 16 as 6, so we stop here. So 6 is now the most significant bit and 10 is the least significant bit. So we write it like this: 10, 6. 10 is the least significant part and 6 is the most significant. 610. 610. Now at the place of 10 we write A, because in binary I told you this 10 represents in hexadecimal the symbol A, so we write 6A. So 6A in base 16 is the conversion of 76 into decimal. Okay. Now let us understand some other conversions also, like binary to octal and octal to binary. First, understand binary to octal. So binary to octal is very simple. You do not need to do any much bigger calculations in converting from binary to octal, because both are the systems of binary. They are actually, binary is a base 2 system and octal, is, you understand, is a base 6 system which is 2 to the power 3. So conversion is very interesting. Let us say 11011. This is in binary and we need to convert it in octal. So the process is very similar. Make the group of 3 from this binary number. First group of 3 bits is 011, and for making this group of bits we append 0 at the end. So the group says 011 and 011. So we make two groups. First is 011, and for making it a group of bits we can add 0. It will not affect the result, so we can append it with 0. So 011 is the next group. Now the result of this group, and this is equivalent to this group, is equivalent to, in octal system, this is equivalent to 3, and this is also equivalent to 3. So we get 33 as the number in octal system. So this conversion is straightforward. You see, the reverse conversion, that is octal to binary, is also simple. As you have guessed, in the octal to binary conversion, we write the number in, let us take one example also. Let us do octal to binary, and the conversion from octal to binary. Now in octal to binary is also straightforward. Suppose the number is 76 in octal. 76 both are octal digits. Now convert it to binary. Now conversion to binary is very simple. Make this number or write these numbers as the group of 3 bits. For example, 6 can be written as 110. Similarly, 7 can be written as 111. So this is the result in binary. So straight away you are getting the result in binary. Okay. Now the other conversions, like binary to hexadecimal. Binary to hexadecimal is also straightforward. In binary to hexadecimal, suppose this is the number. This is the number in binary, and you want to convert it to the hexadecimal. The process is similar to the conversion from octal. See, we make in the octal we made group of 4 bits. Here we are making group of, in octal we made group of 3 bits. Here we are making group of 4 bits, like this and this. So this group of 4 bits, it is actually, what is this? What this value is? Group of 4 bits. This is actually 15. 15 means F. And this value is, we are adding 0 at the left end. It will does not affect the result, and we are able to make a group of 4 bits by adding this 0. So this results into 6. So 6F is equivalent to hexadecimal system. So this is the conversion straight away from binary to hexadecimal. And as you have understood that in hexadecimal to binary conversion, means the reverse conversion, we need to break these individual hexadecimal digits into a group of 4 bits. So we consider this in the group of 4 bits. For example, F we take this 1111. For 6 we take 0110. To make it a group of 4 bits, we add 0 at the end. So 0110. So this becomes the conversion from hexadecimal to binary. So this is the way we can convert these number systems. So this is all about number systems in computer.